Hello and welcome to another video. This time I'm fixing the terrible video I did before where I messed up this proof by failing to add 32 to negative 33 correctly. Thanks Dave Miller for pointing that out. I really appreciate it. It was a terrible, terrible answer. So yeah, I'm going to go through this one again, and like I call it the evil practice paper, but it does have loads of proof on it, doesn't it? Like you look at it, and loads of good questions. They're just hard. It's harder than a normal paper, I'd say, but that's fine. That's good. Like if you're at that stage anyway where you want to, throw everything at yourself, then that's good. But I would say though, practice the basics as well. It's well worth looking at the CGP papers on the same page. They're easier. But, basics and advanced stuff, all of it. Okay, so this first question, I like this because it reminded me of this question which came up in an old Excel paper. Prove arc sine x plus arc cos x is pi over 2. It's 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 really just saying that the angles in a triangle add up to 90 degrees. The two non-right angles in a triangle add up to 90 degrees. That's all it's really saying. But anyway, it reminded me of that, and so the first thing I did was I drew a diagram because arc sine and arc cos are always about angles, and I thought if I call this theta, then I could have like sine theta, for example, equals like if I want this to end up as x, then I'd have this as x and this as 1, yeah? The opposite as x and the hypotenuse as 1. Now let me explain my thinking there. And I know you might be thinking, well, I wouldn't think to do this. I know what you mean. Once you've seen this trick, you've seen it though. And arcsine and arctos and arctan questions are often best done by drawing a triangle. They really are, and labelling an angle and just seeing if you can fathom out what's going on. Now if I do that, yeah, I can say theta, it's arcsine of x. Yeah? Oh, arcsine theta, arcsine of x. I can now label this side y minus 2 for very similar reasons, because I can say cos of theta is y minus 2 over 1, that's y minus 2, and so theta is arc cos of y over 2, y minus 2. And so now I can say as theta is this and theta is that, then this is that, and that's kind of nice. It means that in this situation, this applies. We see that, if you like. Okay, and so now let's use Pythagoras. And you can say that x squared plus y minus 2 squared is going to be 1 squared, and so x squared plus y squared minus 4y plus 4, but take away the 1, plus 3 equals 0. Okay, question 2. Yeah, the one I messed up before. Poor. That's all I can say about that. Yeah, thanks for spotting the mistakes. Any mistakes you see, and there will be more, let me know. Okay, minus 4x plus 4 if you expand it. These kind of questions, often there's a trick you can do in inequalities, which is to show that something's a perfect square. Now, how can we turn this into a perfect square? Well, if we move the 8x over and then make this a 36 on the end, you've got a perfect square there, yeah? It's an old trick. It really is. The reason I've made this sine 2x as well is because I know this fluctuates between 1 and minus 1. So the maximum value now on the right hand side is 0, yeah? And the maximum value on the left hand side, sorry, minimum value on the left hand side is 0. So the only way this could possibly be true is if the left hand side and the right hand side are both 0. If I can say left hand side is greater than or equal to 0, right hand side is less than or equal to 0, yeah? Well, all I've got to do now is check the case where equality holds, and when left hand side equals 0, x equals 6, but sine of 12 doesn't equal 1. Hence, x minus 2 squared, hence the result is true. Is established. Cool. Right, what we got next? This one. Okay, this one's a bit weird, no doubt about it. I've never seen a proof by exhaustion like this. Could come up though, you never know. Okay, so mod of y is 6 minus x. Now immediately I'm thinking x can only be 6 or 5 or 4 or 3 or 2 or 1 or 0. In which case y could be, well, y could be if x, and that's because x is an integer. Yeah, I can see that. And also because y, the left-hand side is 0 or bigger, x can't go to 9, because 6 minus 9 would be a negative number, and that's never true. And so what are the corresponding y values? Well, you get if x is 6, y is 0. If x is 5, y could be 1 or minus 1 because of the modulus. Same here for 2, for 3, for 4, for 5, and for 6. And then you just have to note that the products here are all between 10 and minus 10. And I think in the mark scheme they draw a nice little table and pair them up, which is a good idea. Okay, part A. Proof by contradiction, counterexample, sorry, that the sum of two rational numbers is not always rational. Well, how about root 2 and minus root 2? Because they add to give 0 and 0 is rational. You might say, is it rational? And I'd say, yeah, because it's expressible as a over b, where a and b are coprime, and a is 0. And b is any number you like, b any number you like apart from 0, maybe. Let's not go there. But yeah, you could use that. If you're slightly more cautious, you might use 2 plus root 3, 3 minus root 3. Yeah, just add them together, you get 5. You could use loads of examples there. And explain yourself. Yeah, let's use this one. Maybe you're a bit worried about 0 is being a rational number. It is a rational number, but even if you're worried about it, just use something like this. Consider hence the result is it's not always irrational. You have to be careful with these rational irrational ones. I think sometimes they can be confusing. B. Proof by contradiction that the sum of a rational number and an irrational number must be irrational. Okay, let's start by assuming the opposite. I.e., what's the opposite of this? Okay, proof by contradiction that the sum of a rational and an irrational. I'm sure this came up like last year or a year before. They do ask these. Okay, assume the opposite, i.e. the sum of a rational number. Yeah, let's say consider. Yeah, assume the opposite. And I might even start like this. Let our rational number. Yeah, no, I will start by, because I do want to emphasize to you, it's worth always writing assume first. Assume the opposite, i.e. yeah, make it just real clear to the examiner that's what you're doing. The sum of a rational and let's give that rational a name, a, which equals p over q, and an irrational number b, sums, yeah, I've already said the word sum, let's not say is equal to another rational number c, which equals like m over m. Yeah, and let's just put some conditions on these. P and q are going to be obviously integers, natural numbers if you like, and m and n are natural numbers. But then, okay, b would equal, as a plus b equals c, we could say that b equals m over m minus p over q, which is the same as mq minus pn over nq, and that is definitely rational, which breaks this thing. It breaks our original assumption. B was supposed to be irrational. and it's clearly rational. Hence, our original assumption is false. And the sum of an irrational and an irrational is always irrational. There we go. Okay, I hope that makes sense. That's just the first 3 questions. I'm going to be going through this whole paper because I do think it's got some good questions on it actually, really, on reflection. So yeah, okay. Keep up the hard work. Bye bye.